We've learned that forces can be either contact forces or non-contact forces. Non-contact forces are also called field forces. Contact forces are when two objects are touching each other, they're in contact, one object exerts a force on the other. Field forces include gravitational force, electric force, and magnetic force. And those are the three that we've discussed so far. Gravitational force is only an attractive force. Every object that has mass has a gravitational field around it. And the more mass it has, the greater the gravitational field, the greater the strength of the gravitational field. And again, gravitational force is only attractive. There is no repulsive gravitational force. Electric force can be attractive or repulsive. Electric force is based on electric charge. We have charged particles, protons, and electrons. Protons have a positive charge, electrons have a negative charge, and atoms are made of both protons and electrons. When a substance has more electrons than protons, then the substance has a net negative charge. When a substance has fewer electrons than protons, it has a net positive charge. A a positively charged object and a negatively charged object will be attracted to each other. There will be an attractive force between them. Two positively charged objects will have a repulsive force pushing them away from each other, and two negatively charged objects will have a repulsive electric force pushing them away from each other. So the general rule is that, well, there are two general rules here, is that the magnitude of the electric, uh, the magnitude of the electric force is proportional to the charge. So it's related to the imbalance of protons and electrons. And the second general rule is that opposite charges attract and like charges repel. Magnetism, in some ways, is similar to electric force. Magnetic force can also be attractive or repulsive, and uh, magnets have a, it's not positive and negative, but magnets have a north pole and a south pole. Two north poles will repel each other, two south poles will repel each other, a north pole and a south pole will attract each other. So again, we have opposite poles attract, like poles repel. But the difference here is that magnetism is not based on an imbalance in the number of particles, the number of electrons or protons. Every magnet has both a north pole and a south pole. Every magnet is a dipole. So if you take a, a magnet and you break it into two smaller magnets, the large magnet has a north pole and a south pole. The smaller magnet will have a north pole and a south pole. Now let's look at this image that we see a magnet attracting a chain of steel paper clips. Well, steel is attracted to a magnet, even though the steel paper clips are not themselves magnets. So here's another difference between magnetism and electric force: is that magnetic force can sometimes attract things that are not themselves magnets. It can never repel things that are not magnets. But it can sometimes, a magnet can attract some things that are not magnets. In this case, paper clips, and the paper clips are made of steel. Steel has iron in it, and so the magnet is attracted to the the iron in the steel. But think about this. Let's say each of those paper clips is an inch long. If you put a paper clip 3 inches away from this bar magnet, it probably wouldn't have, if this is like the bar magnets that we use in class, it would not have enough force. The magnetic force would not be strong enough to lift up that that paperclip from 3 inches away. So why are you able to make a chain of paper clips that is able to extend farther than field uh, the field of the magnet would be able to exert similar attractive force? Well, what must be happening here is that the first paperclip that's attached to the magnet is itself becoming magnetic, and then when the second paperclip is attached to the first paperclip, it becomes magnetic, and so on. So instead of one magnet attracting four paperclips, now we have one long magnet that is made up of the bar and four paper clips. If we look at the magnetic field lines, then we see that this is indeed the case. The field lines, instead of forming around the magnet and showing that the paper clips are attracted just to the magnet, we see that when we have this chain of paper clips, then the field lines actually extend from the bottom of the assembly up to the south pole of the magnet. So the field lines are drawn as if this was one big magnet. Now notice the field lines, even though they're extending over a longer distance, they're not becoming more dense. So the magnetic field is not becoming stronger, it's being more spread out over the length of this magnet. So there is a limit to how many paper clips you can hold with a magnet, because remember, all the paper clips are being they have two major forces acting on them. They have the magnetic force holding them up, but then they also have gravitational force pulling them down. And when the gravitational force, or when those competing forces get to where the gravitational force is greater than the magnetic force, then your paperclip chain is going to fall. Iron is what's called a ferromagnetic material. Ferromagnetic materials include iron, cobalt, and nickel. Ferromagnetic materials are materials that can be magnetized when they are in the presence of a magnet. They are not magnets themselves necessarily, or they're not permanent magnets themselves, but they can be magnetized. The prefix ferro actually means iron, but there are other materials that are also ferromagnetic. As I mentioned, cobalt, nickel, and their alloys. So sometimes their alloys include rare earth elements. And when they do, like neodymium, for example, is a rare earth element that's commonly used in very powerful magnets. And so sometimes these alloys actually become more powerful than something like pure iron or pure cobalt. And they can also form permanent magnets like a neodymium magnet. So when we look at these magnetic field lines, we see that they are they are the same shape that they would be if we just had a magnet that was the length of the entire chain plus the magnet. But we see that they are not as close together as they would be if you just had a longer magnet, because the whole structure is not generating the magnetic field. So the magnetic field becomes longer, but does not, or becomes bigger, but does not become stronger. Electromagnets are pretty handy devices, because an electromagnet is a magnet that you can turn on and off. We can create electromagnets by wrapping a coil of wire around a ferromagnetic material, and several coils of wire, and each coil generates its own magnetic field. When you pass an electric current through a wire, it not only does it create an electric field around the wire, it also creates a magnetic field around the wire. And so when you have a coil of wire, excuse me, when you have a coil of wire, it creates an electric field that is strongest inside the middle of that coil. And so when you have several coils, the strength of those magnetic fields add up, and you can, if you have a ferromagnetic material inside that coil, like let's say an iron bar, then that iron bar can become magnetized when you turn the current on, and then it becomes demagnetized, or sometimes it retains some of its magnetism, but it becomes demagnetized when you turn the current off. The more coils you have in your electromagnet, the stronger your electromagnet can be. So you can adjust the strength of the you can adjust the strength of an electromagnet. You can have more coils in it. You can change the number of coils. You can change the current. Remember, increasing the current is going to increase the strength of the magnet because you're going to have a stronger magnetic field around the wire. Or you can do what I mentioned earlier, but you can add a ferromagnetic core that's like an iron bar through the middle of the coils, and then the ferromagnetic core becomes magnetized, and then you actually have a physical object that is a magnet that where you can turn the magnet on and off. Now, another way that magnetic fields can be generated, like in a permanent magnet, there's a mineral, a naturally occurring mineral called magnetite, and that this obviously doesn't have electric current passing through it, or a bar magnet doesn't have electric current passing through it to keep it magnetized. So what keeps a permanent magnet magnetized is the fact that the electrons in the atoms that make up these magnets, well, all electrons spin, and they spin one way or another. And when an electron spins, just like when an electron flows through a wire, it generates a magnetic field. Well, when an electron spins, it also generates an electric field. So in a permanent magnet, I'm sorry, when an electron it generates a magnetic field. So in an electromagnet, or in a permanent magnet, we can get all those tiny little magnetic fields around these electrons aligned to each other, and therefore we can create a magnet. You can make a large magnet with a bunch of tiny little aligned magnetic fields where all the north poles are on one side and all the south, or all the north poles are facing one direction, all the south poles are facing the other direction. And so you get a big magnet that has a north pole and a south pole based on the spin of those electrons. So if you have an electric circuit with a battery and a copper wire, just a regular old electric circuit, just a wire running from the positive to the negative terminal, what is the charge carrier? Well, the charge carrier is the electrons in the copper wire. This is Electrons are present in not only in copper wires, but also in iron. Uh, well, not only in copper atoms, but also in iron atoms. Electrons are in all atoms. Electrons are the same in all atoms. So an electron from a copper atom is no different than an electron from an iron atom. But we know that excuse me, we know that copper is a better conductor. So the copper carries the electric charge, and then the iron, the ferromagnetic core, is what becomes the magnetic part of the electromagnet.